Yeah, there is a question
Yes.
on notation.
Yes.
When you say a to the power a, so superscript a.
Yeah.
How can I understand? Because okay, I understand what a itself is.
A. This is a matrix, right? This is a matrix field. So mu is the Lorentzian index. This A runs from 1 to the dimensionality of the number of generators of the group, right?
Okay.
So for example, if you had an SU2 field, SU2 will take values in 2 by 2 complex matrices. So you're expanding in terms of sigma y, sigma x, sigma z. So that's runs from 1 to 3.
Okay, but a priori we don't know what of those A's are basically.
Well, which A? This?
No, the whole thing.
This is a field. So that's whatever field configuration. Yeah. All right, so let's get started. So today we're going to be talking about non-abelian gauge theory, and I'll do a review, a little bit more extended review of what we discussed in the previous lecture. So in search of four-dimensional interacting quantum field theories, we turn to non-abelian gauge theory. And we said that the Lagrangian density for this theory that's called Yang-Mills, it's interacting, is defined in terms of a gauge group G, a representation R, and a coupling. You need all these three ingredients, right? And here's what the action is: minus 1/4 TR traced in the representation of F mu nu squared. So T of R, hopefully you recall what T of R is. Do you recall what it is? It's related to the Casimir. Casimir is proportional to the identity, the coefficient of which is T of R in the representation R. All right. So the gauge field is Lie algebra valued, hence this label runs over the generators of the Lie algebra. So you could view it as a matrix. An example I gave, for example, SU2 or SU3, this A runs from 1 to 8. And these are the, I guess you haven't seen them, Gelman matrices. But in SU2, it would be sigma I, sigma y, sigma z, each divided by 2. So you could view them as 2 by 2 matrices. These run from 1 and 2. So there's a piece that is just the standard derivative. It's diagonal, of course. And then there's a piece which is the proportional to your connection, right? This is the connection. It's proportional to your gauge field. And these are the Lie algebra generators. Good. So a little bit of representation theory review. I think I called this. Oh, sorry. I think I misspoke. So the trace of the multiplication of two generators, we call that T of R, right? That was the notation. So sorry. I think this is what appears here, right? And then the normalization of so this is the Casimir. This is the quadratic Casimir. Right? It's proportional to identity, the coefficient of which is C2 of R. I think I called it T2 of R at some point as well. I might have called you many different names. So the generators will satisfy this commutation relation. These are called the structure constants of it. In the adjoint representation, we represent the generators by FABCs, by the structure constants, right? So by the virtue of the fact that, so now if that is true, you could easily read off what the C2 of G here means the adjoint representation is by multiplying these two guys, right? So we said that in SUN adjoint representation, C2 is equal to TG equal to N. Good. Questions? All right. Gauge transformation. So under a gauge transformation, A mu of A transforms to A mu of A plus 1/G del mu of lambda A plus this extra term. This extra term comes from the covariant derivative, right? Well, yeah. So if you had U1, this wouldn't be there, right? So it would be 1/E del mu of lambda. this term wouldn't be present. Why is that term not present when you have U1?
The structure process.
Yeah, there's only one generator and commutes with itself. So of course, this is 0. It's not there. When you construct F mu nu, which is this field strength, for precisely because of this term, you're gonna end up with an expression that is like there's a standard looking expression, and then there is this bit that depends on the structure constant, and the fact that it has two terms that are bilinear. It's like second order, and A mu will tell you that this is not gauge invariant. Now, this is the term that ruins gauge invariance. It's absent in U1. That's why the field strength in U1 is gauge invariant, right? So the failure of gauge invariance of field strength in non-abelian gauge theory is controlled by structure constants. So in Yang-Mills, what are the equations of motion? The equations of motion will become d mu of F mu nu of A equal to minus G nu, right? This is current conservation, right? So if you recall, this should be familiar, right? So here, what is J0? J0 is charge density, right? So charge density will have natural in it electric charge, right? Here, similarly, you take out the coupling, G. You put the coupling out. That's just something that can put out. Actually, it's already decided in your form of the Lagrangian. Now, the current conservation becomes d mu of F mu nu of A is equal to minus G nu of A, right? Here's what the equation looks like. Good. Now, what is the non-abelian current? Non-abelian current is precisely what you would think it is. It's made out of charged matter that's charged under the gauge group, say SUN. However, of course, there will be TA sitting here, right?
You say that it is charged under the SUN.
Yeah. Charged matter. So it's what every time you find yourself confused, think about QED. What are the charged particles? Fermion. What does it mean for it to be charged under U1? Same thing here. So here your matter content is transforming as fundamental of SUN, right? And it has charges. We'll see actually today that the fact that it has charge means there would be this vertex.
Thing is, for an elementary SUN, how do we determine the charge?
What do you mean? Charge is a coupling.
Yes.
Charge is a coupling, right? Charge is you don't determine. The short answer is you don't determine, you measure, right? You measure it once, you normalize it. Now you could do RG flow and see where it goes. You actually calculate beta functions to see if the theory makes sense. All right. We talked about the path integral quantization of non-abelian gauge theories. The idea was that we had the gauge fixing condition, which is some condition G of X equal to 0. For instance, the gauge condition that we picked was del mu of A minus omega of A is equal to 0. This is some arbitrary function that we actually path integrated over. And the Lorentz gauge W of X is 0, right? And we also had relations of this type, G of A lambda. A lambda was the gauge transform gauge field. Gauge transform gauge field. So we had two steps. We had to do that. Well, we had to do the path integral over A mu, the gauge field. We split it into two parts. A part that is gauge fixed, and then gauge orbits. These are integrating over all the gauge transformations because this is unphysical, right? So in step 2, so this gauge fixing, we gauge fix using this A lambda of mu of X, and this was we used an omega of A in the choice of gauge fixing. Then we path integrated over omega with Gaussian weight. This whole thing is a gauge, is called arc C gauge, right? The net effect of the arc C, well, then what happens is that here's what the path integral looks like, d lambda dA. There's that, now this integral, this is 1 that stick in there. We saw that there's a determinant coming out, right? The determinant is coming from what? The determinant comes from the fact that these two together, do you remember how the determinant comes about? Well, you can go back and look at it, right? It comes from the change of variables, right? That's where the determinants come from. All right, so the path, the net result of the path, and after massaging the path integral, we got a path integral over the choice of gauge. Now there's this bit of it is gauge fixed to arc C gauge, the net result of which is just a term 1 over 2C del mu A squared. Now these are matrices, right? So the A and the C's are summed over. And then there's determinant 1 over G del mu d mu, right? That's here. In QED, this would be 1 over E del squared. That is a constant and gauge independent. You can take it out of the path integral. It drops out of all correlation functions. In non-abelian gauge theory, d mu, the covariant derivative, has the gauge field in it. Therefore, what you do, the trick that you use is that this is determined, you write it as a path integral over anti-commuting fields that you introduce C and C bar. These are complex fields. They're scalar under Lorentz transformations and transform as an in the adjoint representation of the gauge group, right? Now this guy decides the propagator and the coupling of the ghosts. We call these ghosts to the gauge field. Its role is just to keep track of to make sure that probabilities are conserved. We're not overcounting. All right, any questions here? Now, we started talking about Feynman rules in arc C gauge. That should be familiar. Now, our path integral from now on will be a path integral over the ghost and the anti-ghost matter field. Now we're thinking of a non-abelian gauge theory coupled to matter, per se. And then the path integral over A mu. There's the Yang-Mills action. There's the ghost gauge fixing action. And then there's a ghost. So the Yang-Mills part of it has to do with that there's this F mu nu minus 1 over 4 TR of F mu nu of A. I'm just symbolically writing this way, right? And then there's a matter, so psi bar psi. These are massive fermions, and they're coupled in this way. That's the right coupling, right? You have to promote it to, yeah. This is the gauge fixing term, and then this is the ghost term. So we'll refer to these terms. Using integration by parts, you can write this down as a standard kinetic term for ghost anti-ghost plus this interaction. Right? Notice that FABC, of course, appears in the interaction term. And that's why we have ghosts in non-abelian gauge theories and not in abelian ones. The propagator for the ghost, labeled ghost and the ghost, labeled by the adjoint representation, is just diagonal, delta AB, I over K squared plus I epsilon, because it's just a massless scalar transforming as an adjoint. The gauge boson, the propagator in the arc C gauge looks like this. Hopefully that's familiar. This is diagonal again in Lie algebra indices. The fermion is just good old fermion, right? You will have labels indices as well. The ghost, this is the contribution of the ghost. Now, the ghost and there will be a ghost, anti-ghost, and gauge field vertex that is proportional to FABC. It's pretty clear it has to be proportional to FABC because this has 3 labels, right? Each of these guys are carrying these labels. And then it's proportional to P mu. Why is that proportional to P mu? There's a derivative term. And here's the vertex between the fermion and the gauge boson, which has a TA, right? Because this guy is labeled that. All right, but now you have a 3 gauge boson vertex and a 4 gauge boson vertex and nothing more, right? In the expansion of covariant derivative, well, f mu nu squared, the covariant derivatives that appear. Each covariant derivative can have 0 or 1 A term. So you're going to get a standard kinetic term, a 3-point function, and a 4-point function. So the 3-point function looks like this. It's easiest to draw all these momenta flowing in, right? So there's A, B, C, mu, nu, rho. Those are Lorentz indices. And the momenta are flowing in. It looks like the following. G is the coupling, of course. It will be related to G FABC. FABC can guess by the number of adjoint labels. Then it will depend. The structure is kind of interesting. It depends on pick K, where K and P. So label all of them to be inwards. K minus P, P minus Q, and Q minus K. And their appropriate number of flat space metrics to contract the for the Lorentz indices. For the 4-point function, you don't need to worry about momenta, right? There's no derivative in there. Remember that this term has one derivative. Why? Because in the expansion, the covariant derivative either gives you a derivative or an A. So if you had 3 A's here, you still have one derivative. Here, you have 4 A's, so no derivatives. So you don't need to worry about momenta, right? So here's what it looks like. First of all, it's order G squared, because every covariant derivative comes with a G. Sorry, the piece of the covariant derivative that has an A comes with a G. There will be now multiplication of structure constants. So it's second ordering structure constants, and this is the structure. All right, questions? So where are we gonna go with this? Where are we going with this? Today, what we're gonna do is we use Fadil Popov to write down the action in a nice way, write down the path integral formally in a nice way. Today, we're gonna talk about how to go about quantizing this. Now we need to be careful as what it means to be gauge invariant, right, at the level of the quantum theory, because we enlarged our theory. There's this unphysical Hilbert space. Now we have to have a rule for what is a physical state, right? So we're going to do that, and that's using a formalism called BRST. That's the most elegant way of doing it, and it relates nicely with ideas from topology, cohomology, all of that. This actually nicely ties in with lattice models as well. That's one thing that we're gonna do. We'll do something else as well. Oh, we're gonna calculate the one loop corrections in this theory, Yang-Mills coupled to matter. So what were the diagrams in QED? What are the diagrams actually? Can you guess? Actually, we'll get that. Let's do BRC first. So BRC takes a little bit of getting used to. Let me tell you first what it is. In essence, what it is it's a very elegant method of repackaging gauge invariance in terms of a symmetry with anti-commuting generators, fermionic generators. So it's a symmetry transformation that transforms bosons to fermions. In particular, what is the fermion that you have? Here, the fermion that you have is the ghost. So we'll go through that step by step. First thing is a trick. The trick that we first use is that instead of, look at the gauge fixing term. What was the gauge fixing term before? It was 1/2 C del mu of A mu, right? Now I introduce a new auxiliary field that looks like this. Is coupled to a mu, del mu a mu. If I perform the path integral over BA, I get the old term. Why? Just completing the square. Just complete the square, right? If you complete the square, you could view this, the path integral over BA could be done, and what comes out is just a term that you use to complete the square, and that's the term we start with. So far, you've seen this trick being used over and over again in Gaussian integrations, right? Gaussian path integrals. If you have a field which is second order, if it's actually second order, you could just perform the path integral, right? And it's we often use this. There's this very okay. There's Stuckelberg method. There's a lot of methods of this type, this flavor that we use. It's just Gaussian integration techniques. All right. Good. So here's our gauge transformation. Here's the action we're going to work with. This B of A is a new commuting scalar field that carries the adjoint representation of the gauge group. All right. So what are your fields? You have the fermion, you have the gauge field, you have B's, we have ghosts, anti-ghost. Okay. Let's do an infinitesimal gauge transformation proportional to the ghost field. I claim. So what is that? What does it mean? It means that what was the gauge parameter that we had? It was lambda A. I'm gonna pick lambda A to be epsilon C of A. C of A is a ghost field, right? Now, because C of A is fermionic, it's anti-commuting. Sorry, it's anti-commuting. This epsilon better be anti-commuting as well. Why? Because your lambda A is what you're shifting the gauge field with. Gauge fields are definitely commuting. So you need two anti-commuting things next to each other to get the right statistics, right? All right. So if this is a gauge transformation, well, del mu of A is this. Is that familiar? Because how does A mu transform under gauge transformation? A mu of A goes to A mu of A plus B mu of lambda A. This is what I'm calling delta to A. And there you go. Right? Similarly, the gauge, the matter field, the fermion will transform this way. That's just a consequence of the gauge transformation, and I picked this variable. Now, for the rest of it, the gauge field itself transforms this way. Sorry, the ghost itself transforms this way. The ghost anti-ghost transformation is proportional to B of A, and B of A doesn't transform. So I don't expect you to see how this is built. But let's just take it at face value. This is some transformation someone is given to you. We're going to see step by step that this is a symmetry. And we're going to explore its consequences. First of all, one important thing to notice is that the general structure of this transformation is any field that you have is epsilon, some anti-commuting thing, some matrix multiplied by other guys. So it's a linear transformation of your fields with an anti-commuting factor in front of it. The most important thing about this transformation is that it's nilpotent. The charge that generates this is nilpotent. Why is that? It's proportional to something that's anti-commuting. Anti-commuting squared is 0. Right? So that is the idea. The idea is to have an operator that squares to 0. And you do that by introducing this anti-commuting variable. All right, everybody's with me? We're going to go through this step by step and see why this is symmetry. Let's start simple with these two terms. No, actually, let's go through this. Good? All right. So let's start with the first two terms. The first two terms are obviously independent. invariant under the transformation. They don't have the ghosts in them. They don't have the B fields in them. It's just these two terms. And the transformation of these two terms is just a gauge transformation. So they must be invariant. Right? This part of it is just a gauge transformation. Doesn't matter what the variables are. So these two terms are obviously invariant. What you need to worry about are, so these two are invariant. There's this term. What is the transformation of this term? 0. BA doesn't transform. So the last two terms are the only things that we need to worry about. Right? As a matter of fact, the action, all that action is designed in such a way that these two terms or transformations cancel. The transformation is designed precisely with this goal. All right, so let's see. So check, actually, you know what? I think I'm gonna give it as a homework thing. Check that the transformation of these two fields cancel. Just plug them in. You'll see that when you check that the transformation cancel, the cancellation is non-trivial. It follows from the Jacobi identity. Okay, it is a symmetry. So just you need to work it out explicitly. In principle, yeah, okay. In principle, the idea is something along these lines, that every time you have a symmetry transformation that relates bosons to fermions, or something commuting to anti-commuting, it's the coefficient of the transformation will have to be anti-commuting, which means that the corresponding charge is nilpotent. This is the lesson to learn. That's extremely powerful. Okay? That's already your connection to topology. We'll go through that. Questions? Is it clear why Q squared is Q is nilpotent? Q squared is 0. Okay. We are interested in gauge invariant states. A gauge invariant state must be killed by Q. This Q transformation, Q is the generator of this transformation. This transformation at the end of the day is a gauge transformation. So any gauge invariant state must be killed by Q. So states of psi that we're writing down, these live in this unphysical degree of a Hilbert space. And these Q, we're going to use it as a way of characterizing what is physical. Right? Now, any vector psi that is killed by Q can be written in this form. It's either some vector that is directly killed by Q, or it's some vector which is, or it's Q acting on some vector. Just act with Q on this. If Q kills the state, that's 0. And then because this term is Q of something, Q squared will give you 0. So this is true. Good. Now, from this point of view, the Hilbert space splits into 3 parts. There is a subspace of states where Q, well, it's not 3 parts, sorry. There are 3 subspaces we can talk about. There's a subspace of states that are not killed by Q. They're not annihilated by Q. That's what we're going to call H1. These are the vectors we're going to pick here. Eta belongs to H1. H0 is a subspace of psi naughts that are killed by Q, but psi naught is not Q of something else. That's this vector. And then there are the H2, which is a subspace of states that are Q of something. These are very familiar from topology, cohomology, if you've seen it. But it's just logical, right? It's just this is the structure of it. For this to be invariant, Q has to kill this guy, and then we're making the separation. Q is obviously going to kill this guy, and we're making the separation between the two terms by saying that this is killed by Q, but it's not itself Q of something. This is killed by Q, but it's because it's Q of something. Good? Now, why are we doing this? Because states in H2 have 0 overlap. Think about 2 states in H2. Each of them is Q of something. So there's Q here, there's Q here. You get Q squared in the middle is 0. In particulars, these states have 0 norm. They're unphysical. They need to be discarded. But it is obvious why it's unphysical, because you found it by the action of gauge transformation, right? It's pure gauge and unphysical. H2 is pure gauge and unphysical. Good? You see the power of this nilpotent operator. If you have a nilpotent operator, you apply it on a vector. If the result is some vector, that vector has to be thrown out of the Hilbert space because it has 0 norm. Right? That's the power of it. The physical states are transverse gauge bosons. They belong to H naught. The ghost and the components of the gauge field along K mu belong to H1. Sorry. The ghost belong to H1, and the components of the gauge field along K mu belong to H2. Components of the gauge field along the direction of the propagation are pure gauge. They belong to H2. Ghosts belong to H1. What is H1? These are things that are killed by, these are the subspace of states where Q acting on it, they're not annihilated by Q. That's the raison d'etre of ghosts. In principle, we didn't have to have them, right? But it makes it to make the theory local and nice. That's why we did. Yeah. This is actually maybe another thing that I should say. The reason we introduced ghosts was locality. We wanted a local action. Determinant is this object inside the path. We don't like that. We want to write it as something local, right? So we introduced the gauge field because there was a theory that the non-locality wanted to make it local. But then when the theory was non-abelian, that was successful when the theory was abelian, but it was non-abelian, it was not successful. There was an extra determinant term. Again, by insisting on, because we want to insist on locality, we exponentiate and write the local term. The ghosts are exactly that. Yeah.
Because if ghosts are just mathematical, tool, they don't exist in physical reality.
What does that mean? What does that mean? It's part. If you're asking, the physical statement is this: ghosts cannot be an external leg in a diagram. It's not an asymptotic state in the S matrix. That's it.
So then they may exist in nature.
No, what does exist mean?
They can be observed.
Yeah, I mean they're not observable. I mean, they cannot exist as external legs. So yeah.
Getting it everywhere is if you didn't include them, then you would not get the right answer. So in essence, maybe they exist, but it's
another way of saying is that the theory, it's the same with gauge field. The theory is non-local. We have to introduce this unphysical degrees of freedom called ghost because we want to describe everything locally. Now the distinction between the good old gauge field is that the gauge field could be an asymptotic state, or you could have a photon, because the gauge field had physical components. The gauge field was not pure gauge, right? But these guys are pure. They're purely because of gauge transformation, right? There are no physical degrees of freedom for these guys. So in that sense, if you want to say they're not physical, they're not. Yeah, but it's just insisting on locality. You have to invent all sorts of weird stuff because you want to insist on locality. You don't have to, but then good luck solving the theory in a different way. Would love to see that. If there's actually it's like I remember somebody poses, a very famous physicist poses as a challenge in a Tazi lecture that, like, if you could do this in a different way, publish it, and just get a flight to Stockholm. People will love to see that. But this is what has come out of lots of many years of work. It's a method that works. It's a deeper history behind this. So there's a deeper understanding of this. Mathematically speaking, Q squared equal to 0 allows us to build the Hilbert space using cohomology. This is a set of fancy words that is that underlies this story that I told you. H0, H1, and H2, and this stuff. So there's a beautiful cohomology theory, topology, that tells you about BRC, that's the space of physical states. All right, questions? Homology is also related to topology. Cohomology is a dual object. Homology is related to topological theories. There often appears in topological theories. But anyway. Oh, that's a challenge for you guys. You could see it explicitly. I did not say it. Yeah, very good question. This was just I stated this factually, but you could see that. How do you see that this bit of it, the component of the gauge field along K mu belongs to H2? Well, think about it. This you could establish very explicitly. Okay. Questions? You know how to say that the second part of it is easier. The component of the gauge field along K mu, why does it belong to H2? So H2 are not ghosts, right? Why does it? Yeah. I think, well, there might be different ways of saying it, but for me, every time I find myself confused, I go back to QED. Right? In QED, there are no ghosts. You still have this unphysical degree of freedom that's propagate. There is no degree of freedom for the gauge field in the direction of the propagation, right? And ghosts go to H1. So now your task is, you have answered this question if you can explain why ghosts go to H1. But that you can also know, right? Look at this. What is a Q transformation? Right? I mean, that's by design. Again, when the first time you look at BRST, it looks ugly. It doesn't seem to be any there doesn't seem to be any elegance to it, but it's actually quite elegant. All right, good. Okay, no, I don't want to show this. I want to ask questions. So let's go back to QED and let's ask about one loop diagrams. So what are the things that we're going to calculate at one loop? Now we have our gauge boson 1pi diagrams at one loop. What else should I draw? The fermion. And then what else? The vertex, exactly. Tell me what these contributions are. This guy. So previously, yeah, what did we have for the case of QED? We call this vacuum polarization. We had this guy. Now in the loop, there are a couple of different fermions that run, right? And every fermion gives you -1, right? You just have to add them up. What else is there?
The gauge boson.
Tell me what it looks like.
So wiggles.
Okay, what do I do?
They connect like a circle.
Like this, right? What else is there?
The same thing.
Because they have 4-point function. What else is there? Okay, I'm not gonna bother you. You missed one. Ghost anti-ghost. For the fermion self-energy, it's the same old diagram. That's the only thing you can draw. So the gauge boson self-energy are these diagrams, these 4 at one loop. Fermion self-energy is still the same one. Now, the boson fermion interaction, the vertex, there are actually two terms now. This is familiar from QED. This is funky, right? Of course, we're drawing one PI diagrams, right? All right. Is that clear? Questions? We're gonna calculate these today. You might think that this seems like very, very difficult. Well, it seems like ugly. It is actually kind of ugly, but if you've done your homework, QED homework well, some integrals you see, just copy the answers.
The momentum exchange is the same.
A lot of it is similar. There are some brand new features. So like you see, this diagram, you have a very good idea. You have done something like this in 5-4 theory. This diagram, you know exactly what it looks like. This diagram, you also know what it looks like. So these diagrams are not genuinely brand new. So you could recycle your old calculations. Here, the only diagram that is like really genuinely new, so I'm looking, is this one. And of course, the vertex is always complicated. All right, what are the counter terms? There is the gauge field propagator counter term. This is what it looks like. There's a fermion mass counter term, and then there's a vertex counter term. You gotta put the A's and stuff, right? As before, there will be word identities that relate the counter terms. Do you have a question? Oh, there are word identities that relate the counter terms. So in QED, there were only two independent counter terms, right? The word identity, how did it relate the counter terms? So what is the relation that it was? Yeah. The propagate, yeah, exactly. The vertex was related to the fermion.
Are we considering massless fermions?
No, they're massive. So was the case in QED.
But the counter term should have some delta in there.
Oh, that is, well, okay. So very, very good point. The calculation we're gonna do, the reason I'm doing the calculation is that I'm after beta functions. And if you recall, in beta function, you treat mass also as a deformation. That's why I'm being a little bit, yeah, correct. Good point. So I have in mind a simplified version, right? Okay, so let's start with the gauge boson self-energy. Seems like it's a lot of diagrams, but it's pretty straightforward. So what does the word identity say? It says that if you contract Q mu with this guy, the full 2-point function, you're going to get 0. That means that it has to be transverse. It has to be proportional to this index structure multiplied by pi q squared. If you recall, what happened in QED was that the word identities, when we did the one, this guy, when we did this, in this diagram, we found some awful lambda squared divergences in vacuum polarization, and word identities made sure they disappear. Then everything remained log divergent. Similar thing will happen here, right? Exact similar thing. But I'm going to present it now that you're a little bit more familiar with dimreg. I'm going to present it in the context of dimreg. How do you see a log in dimreg? Yes, but you see it as something that has a pole as d goes to 4. In particular, it appears as like something that's like gamma of d minus 4. In dimreg, the structure of it was that something that has a pole as d goes to 4, right? A pole in 4 dimensions is log. What is a lambda squared term? How would you say it in dimreg? It's a pole in 2 dimensions, right? It's a pole in 2 dimensions. Because the number of the things down in the integral and the things that are up in the integral are the same. So in 2 dimensions, if you find a pole, that is precisely the same awful divergence that word identities must take care of it. We'll see that explicitly, but this time around, I'll just do dimreg, and then you'll see that. Okay? So here's the answer. for this diagram. Let's just break this down. This you could have guessed, right? This obviously is there. Now, does this look familiar? This is exactly every single thing here is the answer for this diagram in QED. The only difference over there was that up here we had 2e squared over pi. I think something like that. But here what you have is 8, and then this is 2, right? So 8 over 16. Oh, I think, yeah, 8 over 16. And your g squared, I think what I coded is 2 alpha over pi. Let me write down that. So what is inside the integral is the same. Let me write down the QED answer. The QED answer is 2 alpha over pi, you have x minus x, exactly the rest. Right? So alpha is e squared over 4 pi, right? E squared over 4 pi, 2 pi squared. This is e squared over 2 pi squared. Make this g, right? You have 16 down there and 8 up there. I cancel. So this diagram, you don't need to do any new calculus. You just rewrite it. Good. Now, of course, it's tricky. There are NF fermions. If you have NF flavor fermions, they're all run in the loop, and you have to multiply by NF. What is this? There's a minus sign, and it has to do with the fermion loop, right? Okay. Now I'm just writing the answer for it in the C=1 gauge. So there's minus g squared over 2. That shouldn't surprise you. G squared over 2. There are 2 vertices. C2 of g. Where does this come from? What is C2 of g? C2 of g comes from it's the adjoint so Casimir, quadratic Casimir in the adjoint representation is proportional to identity. Is the coefficient of that. In the adjoint representation, the Lie algebra generators are FABCs. So this is coming from the fact that in this term we have 2 f's multiplying. That's the origin of this. You have to do these calculations a little bit, but you can see where it comes from. This bit of it is like, what have I done? I've basically done my change of variables, Euclidean path, weak rotation, Euclidean signature, and then I've done my Feynman parameters. These steps up to here. The rest is just vertices, right? So what were the steps? We would always do these, right? So we first do dimreg, then we do a change of we do Feynman parameters, then we change variables to L variable. We go to we do weak rotation, and then that's where I've stopped here. This is the index structure up here. This factor of 2 comes from symmetry. So as I said, I've done dimreg, Feynman parameters, and defined L mu, which is K mu minus X Q. This is the simplest Feynman parameters possible, right? It's just like 2 terms down there. There are 2 propagators in the loop, so you only introduce 1 X variable. This is what it looks like. Now, I'm gonna massage it a little bit and write it in the following way. So this delta is the thing that's down here. Well, okay, sorry. Let me explain a little bit more. In this expression, what I've done is that, well, I've done the integral over L and taken out gamma functions, right? I've written them in this particular way. I want to emphasize this term, which has a pole at d equal 2, and these 2 terms that have a pole at d equal 4. This means awful. This means terrible, right? This means this is highly unphysical. As a pole in d equal 2 is exactly that lambda square term that gave us hell in QED, and we do know that it's going to get cancelled by more data. what are the things that are going to kill this term? These are the two terms that will survive, and they're log divergent. Okay. So how many diagrams have we done so far? We've done this diagram. It has a log divergent term. We have this diagram that has this awful divergence. Now there's this guy. Similarly, I'm not going to bother you with the details of it. I've done all those steps, done the L integral. There is a pole in d equal 2 and a pole in d equal 4. Similarly, you do this this loop diagram. You see, it's very structurally very, very similar. Like the terms that appear, the combinations, if you play around with them, they're very, very similar. You basically have one basic integral for all these diagrams, and the rest is just like kinematics. Again, you have a d equal 2, d equal 4. The signs matter. Here's minus, 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 plus, plus, minus, and yeah, whatever the other one was. All right, once we all do these diagrams, we put them all together. We're gonna look at the pole at d equal 2 first. Now, the beauty of the ghost is that once you introduce ghost, word identities are automatic. In fact, when you sum up the coefficient of the three diagrams, the coefficient of the 1 minus d over 2, the total coefficient that sits in front of it is d minus 2 times 1 minus d over 2. This will cancel the pole here. So as so this term is smooth as d goes to 2. Similar thing, well, I think I mentioned that. So the ghosts make this pole disappear. All right. This is a detailed calculation. I'm summarizing it for you guys. And in your homework, you're going to do some of these calculations. They're not, this is actually not brand new. All these diagrams are pretty straightforward. You have to get your hands dirty, but depends how much you actually worked on the QED calculation. All right. Now consider the coefficient of the term, which is the gamma of 2 minus d over 2. Oh, by the way, one more thing to say. This gets rid of the pole at d equal. Well, actually, no, that's not. Let's look at the poles at d equal 4. So the log divergent terms. This is the coefficient of it times the gamma function 2 minus d over 2 eta q squared. This is inside the x integral, right? I haven't done the x integral yet. I usually don't do the x integral until very, very end. If you recall in QED, we use this thing that there is a symmetry sending x to 1 minus x, right? That means that the terms in linear in x could be written this way. That could be used to simplify this expression. We use exactly the same trick, perhaps less complicated in QED. After that, all the dust settles. This is what the combination of the log divergent term is. 1 minus d over 2. This term that will give you log divergence, q mu q nu. 1 minus 2x squared minus 2, all of that. This is a coefficient. This is fun. Now, you might wonder, why q mu q nu? Because I'm in c equal 1 gauge. Right? There was q mu q nu minus 1 minus c q squared. I'm in c equal 1 gauge. So I'm doing this because I'm trying to make my expressions shorter. I could work in whatever gauge I want. So here are the three diagrams put together. Now I put it back. Now that I know that this, you know, like the gauge dependence of it is, I'm going to write it this way. Right? This is required by word identities. This is the coefficient of it, and this is the structure of the divergence. It's the log divergent part of the story. As we discussed earlier, we're going to try to extract beta functions from this next few lectures. That's why we're doing this calculation. Good. Questions? Okay, so now you still can do a little bit better, but I don't expect you guys to see this step right away. It is some calculation. The UV divergent part of what this expression is looks like this. In particular, what is important from this calculation, so I put a y here. So for looking at this expression, you could extract out the UV divergent part of it. It looks like this. Well, you wouldn't be surprised that this gamma is there, right? The thing I want to point out is that if you do this calculation, you get -5/3. You repeat the calculation RKC gauge, and you find that this is actually KC dependent. So there's some gauge dependence here. You have to be careful with. Okay. In summary, what did we talk about? We talked about non-Abelian gauge theory. We wrote the action, which is base of R, F mu nu, F mu nu. This is a non-Abelian Yang-Mills action. Then we had coupled a fermion to it. Then there was, I think, minus a gauge fixing term. Actually, I think how did I write the gauge fixing? The d mu, right? Yeah, I think I wrote d mu. There's a gauge fixing term. So it's Yang-Mills, if you want. This is fermion kinetic term, fermion kinetic term. And then we had the ghost anti-ghost, right? Which schematically looks like, well, actually, there is a kinetic term for the ghost anti-ghost, if you wish. And then there is a term that couples CCA. You could write the whole thing as a del mu of the covariant derivative, right? And this is all the matter for content. This is the ghost anti-ghost. The physics of it is exactly the same, right? And then we did the in BRST, we introduced a Q transformation. Q transformation is before we talked about the gauge transformation, which is proportional to the ghost. This is the very definition of BRST. If you have a gauge theory in quantization, if anyone asks you what BRST quantization is, you say you take a gauge, non-Abelian gauge theory. It has to be non-Abelian, right? Then you take a gauge transformation that's proportional to the ghost. The coefficient of that must be anti-commuting. The corresponding charge is going to be anti-commuting, which means the square is to 0. Now, because of that, the corresponding charge acting on a vector giving to 0, this is a physical condition. And this in large Hilbert space, you learn that you could write this down as, I don't remember how I wrote it, but so let me say psi naught plus q of psi 1. This is the most general vector that's killed by q. This guy is q of psi naught is 0, but psi naught is not q of something else. This is the Hilbert space. We call H naught. These are purely physical. This is what we're after, right? This term, psi 1 is not killed by q, right? But this term obviously is going to get thrown out. So these are the purely physical things. These have to do with a ghost, anti-ghost, right? Then the vectors like this, so sorry, these guys have to be close. The vectors like this that are themselves Q of something, they have zero norm. They're pure gauge. They are like the direction, the direction of the degree of freedom in the gauge fields along the direction of propagation. Yeah, I just made a cryptic comment about cohomology, and then we started the quantization of the theory. We looked at the Feynman diagrams that we had. We wrote the Shannon terms. We're gonna, yeah. So the diagrams that we looked at are this guy, and well, we haven't looked at this one yet. Right? The structure of this is very simple. So there's a ghost that runs in there. There is a fermion that runs in there. There is a gauge boson that runs in there. And then there is this thing like lambda phi 4. This guy is a good old diagram. Right? There's nothing else there. And this guy had the old thing we had, right? And one extra contribution that, let me draw it like this. What we did so far today is we looked at these terms. We extracted out, we saw two types of divergences. One where there were poles at d equal 2. We said those are highly unphysical. They're offensive. They're offensive. They can't. Why are they offensive? Do you remember how we argued in QD they are horrible? They give mass to the gauge boson. Right? That was the problem, right? In QED, we said that if these terms existed, they make the photon massive. And that definitely violates gauge invariance, right? So we said it can't be there because of that, and we looked at coordinates. Here, what took care of it was this diagram. If you ignore the ghost anti-ghost, you did the calculation, you find that divergence. This is exactly what happened in QED. In QED, we didn't have ghosts. So we did the calculation, we found this term, and then we had to say, oh, there was this word identity that we had to be careful with. Right here, introducing the ghost automatically takes care of it. It just cancels that term. The other thing, after we did this, of course, now it's all log divergence. We look at, and I think maybe this was a good lesson. And in dim reg, we talked about log divergence, right? But the log divergence in dim reg often comes from gamma function, which is d minus 4. Or, right, it could be, depending on how you play with it, it could be 2 minus d over 2, right? But that's the pole structure of it. That's the pole structure of it. And the way, well, there's a pole in the equal 2 here as well. So the pole structure of it is actually that, like if you remember when I talked about log divergence and all of that, we talked about sharp momentum cutoff, powers of lambda. In dim reg, the analog of that is poles in what integer space-time dimensions, and you have all of them basically starting at the worst, going down. If these poles are to disappear, the way they disappear is that the coefficient of the pole. So if it's a gamma function, gamma of d minus 4, what comes out of it is d minus 4, right? That will cancel the pole. That's the structure of it, and we ended with this cryptic comment to say that if you just took these diagrams and tried to extract out the divergent piece of this, why would you try to extract out the divergent piece? Because you would want to perturbatively normalize this here. You want to do perturbative normalization. You will find some gauge dependence. So to be very careful, you do this in RKC gauge and keep track of the coefficient. Right? So this was the calculation that led to minus 5/3 is C equal 1. If you do it in RKC gauge, it gets 13/6 minus Qc over 2. Therefore, Qc equal 1 gives you 5 over 3. Self-energy is gauge dependent. Oh, this was a message. I made this cryptic comment to say that self-energy of the gauge boson is not a physically meaningful statement. It's gauge dependent. There's a lot of, yeah. Right? Okay. Any questions? Right, if not, yeah.
Sorry, when you say that the Fermi's energy is gauge dependent, and when you say, okay, that is a non-physical statement. Physically, does it mean, I'm sorry if this sounds dumb, but does it mean that Fermi's energy is just not a hallucination we're doing?
No, this is where we're talking about the propagator of the gauge boson.
Yeah.
Right? No, it's just at some level, gauge boson itself was introduced because we insist on locality. So what is this? It's a 2-point function of a field that propagates locally in space-time. This field didn't exist to start with. It wasn't there. The theory was non-local. We introduced this to make it look local. That's what the issue is, right? So the price you pay for the price you pay for insisting on locality is that at the end of the day, you have a theory, correlation functions, all fields are local. You end up writing everything in terms of local fields. But then there is a dictionary that needs you need translation to go from correlators you wrote down to what you see in the lab. Right? So you introduce all sorts of degrees of freedom to insist on locality, but at the end of the day, because you introduce those, you need to massage your final answers to transform them into things that you observe in lab. This is generally a theme in a lot of times it's a thing, well, for sure in gauge theory, but in physics more generally, broadly speaking, this is an issue. Yeah, in quantizing a theory, we introduce all sorts of you have to make a lot of choices, and those choices are often a matter of convenience of how you're going to go about doing the path integral, right? And once you do that, you end up the output of the path integral is better organized because your forced locality is best organized in terms of the local fields. But local fields were not there, right? You introduced them, so you have to turn them back to you. So a very good question is the following: no physical observable. Think about physical observables of non-Abelian gauge theory. Actually, by the way, what are the physical observables of non-Abelian gauge theory? I think I made a statement that might have confused you guys before. What are the physical observables of non-Abelian gauge theory?
Yeah.
F mu nu is not there, right? So what are the observables? Wilson loops are some. Do you have any local observables? You do know some local observables. What were why, if I come to you and say I have a local theory, what are the most simplest, most obvious observables you would expect to have? No, simpler than that.
Charges.
Energy density. You would expect to have energy density, right? How would you find energy density? Think about your Lagrangian density. Your Lagrangian density was gauge invariant, right? Where does that appear? That term, trace of f squared, in QED is a term that became e squared plus b squared. The thing that is, so now what happens in non-Abelian gauge theory is not, you have a Casimir. So your Casimir is second order. It's not e squared plus b squared. It's something that looks like TA times TA summed over A. Every TA, of course, is like gauge dependent. It will transform in the adjoint. It's like a gauge field kind of thing, right? But the Casimir is a physical thing. The Casimir is a physical thing, and that appears in your energy density. If you just, well, it's actually a very complicated story. of how to construct Hamiltonians for these theories. But that isn't observable, right? So in general, given a representation, all the traces are going to be observables, right? Why? Because trace, you can commute the UU dagger. Anything that transforms the adjoint, you could shuffle the TNT daggers. So those are local observables. But now you also know how they're going to be related to your Wilson loops. Okay, hopefully you know that. The flux that goes through it will be captured by the object outside. Anyway, so in general, to build intuition about a lot of gauge theory phenomena, I recommend, besides these calculations, try to build intuition. Ask this kind of question: what are my local observables? Right? You have all the tools to answer this question. Right? The theory is super transparent. Deep in the UV, this is going to be the functions that are positive. Negative. Deep in the UV, the theory is weakly coupled, so you should be able to answer these questions. The phase structure of these theories deep in the IR are complicated. That's an important unsolved problem. Yeah, we're going to see that it's $1 million problem. Nobody knows the answer to it. Mass gap. QC, Yang Mills, pure Yang Mills, no matter. So it's going to have RG flow. It's well defined. We're going to see it's going to be well defined in the UV, because the beta functions are negative for large enough. Anyway, in the infrared, the coupling is going to grow. You could do perturbation 3 to 1 loop, 2 loop, but all of that is not going to help you. What happens deep in the infrared? What are our guiding principles? Like non-perturbatively, we know very little. Symmetry, basically. So people have studied super symmetric versions of gauge theories. We've learned a lot of things about them. Or you could make your gauge theory large N. Those are methods to go deep in the infrared. But for realistic theories like Yang Mills N equals 3 out there, nobody knows. In experiments, from observations, we see there's a gap. The system opens a gap. There is, and it should be shocking. It should be absolutely shocking. It's called dimensional transmutation. Take QCD, pure QCD, SU3. The Lagrangian has no dimensionless parameter. Has no dimensional full parameter, right? Dimensionless parameter. So you would think under the RG flow, all that's going to happen is that the coupling will grow or become small or something. But if the coupling is dimensionless, how is it going to tell you about a dimension where something is going to, at some energy scale, where something's going to go crazy? That's called dimensional transmutation. If there is for the theory to open a gap means a mass scale. A scale invariant theory has to pop out of it. It's not scale invariant, but the action formally didn't have scale. Has to come out of it due to quantum mechanics. It has to be quantum mechanical phenomenon, a scale. Quantum mechanics will have to cook up scale for you. There are lots of open problems about this. There's a lot of progress around this, using, again, like other simple models, lower dimensions. But Yang Mills deep in the infrared is perhaps the most important problem, unsolved problem of quantum field theory.
What you said is that people were abandoning QFT because it didn't work for QED. What alternative were they contemplating right now? What can you have that isn't QFT?
That's for historians of science. I do not know. I do not know because I was born after that time. But
nowadays we don't have any alternative.